Okay, this is the last part for chapter 4. Okay, so in this last part, we will learn about turbine. Okay, so basically, in the beginning of this chapter, okay, so the definition of turbine is a device that extract energy from a flowing fluid. Okay, so which is different with pump. Okay, for the pump, the for the pump, the energy is referred to the energy produced from the for example from the shaft or from the top of the shaft and then produce the power of the for the fluid. Okay, so there is for the pump. So the geometry of turbine is such that the fluid exerts a torque on the rotor in the direction of its rotation. Okay, so the shaft power generated is available to drive generators or other device. Okay, so you can find this turbine, for example, in how to say it, hydro electricity power plant, and then in the aircraft, for example, it is a gas turbine engine. Okay, so there is example for the turbine. As you can see in this figure, there are two common types of turbine, which is the first one is impulse turbine, and then the second one is reaction turbine. But before that, before I forgot, the main difference for this turbine in terms of efficiency is uh, for for the pump turbine efficiency for the T refer for the turbine. It is power produced from the shaft, which is W dot shaft divided with P power from fluid flowing fluid. Okay, so this is how to define the efficiency for the turbine. Okay, if you recall that for the pump, efficiency is power from fluid divided by W dot shaft. Okay, so rho G H pump Q divided by W dot shaft. Okay, so this is that you have to bear in mind how to define the efficiency for the turbine. Okay, let's move to the type of turbine. The first one is impulse turbine, and then the second one is reaction turbine. So why we call it reaction turbine mean that it is related to reaction turbine, it is related to the ratio of static pressure drop that occurs across the rotor to static pressure drop across the turbine stage. Okay, so there is reaction turbine. So for the reaction turbine, a larger rotor pressure drop corresponding to a larger reaction for that turbine. Um, So for the impulse turbine, as you can see in this figure, okay, so this figure, it is known as a Pelton wheel turbine. Okay, so this is known as Pelton wheel impulse turbine. So in this turbine, the total head, which is defined total head, which is defined from the sum of the pressure head, and then velocity head and elevation head, which is from Bernoulli equation, is converted into a large velocity head at the exit of the supply nozzle. Okay, uh, or nozzle. For example, normally it is coming with a lot of nozzle for the impulse turbine. Both the pressure drop across the bucket or blade. Okay, so as you can see, this is bucket. For the turbine, we call this as a bucket, and then also we can call as a blade. And the change in the relative speed, which is fluid speed relative to the moving bucket of the fluid across the bucket, negligible. Okay, so the space surrounding the rotor is not completely filled with fluid. So it is the impulse of the individual jets of fluid striking the buckets that generate the torque. Okay, so this is uh, power. Sorry, the flowing fluid. Okay, that exit the bucket and then produce torque for the rotor. So this is the turbine. So this is the most easiest type of impulse turbine, which is known as Pelton wheel turbine. Okay, so as you can see from the this view from above, from this view, you can see there are uh, deflection of velocity. Okay, so we can define the relative velocity, which is W, and then we also can define the absolute velocity, which is V, and then U is the rotational velocity for the rotor. Okay, so as you can see here, so V1, which is the absolute velocity, a high speed jet of water strike the Pelton wheel here, bucket, and is deflected. Okay, so this is deflected. The water enters and leave the control volume. Okay, so this is the control volume surrounding the wheel as free jet, which is the atmospheric pressure. In addition, a person riding on the bucket would note that the speed of the water does not change as it slides across the bucket. So that is the magnitude of relative velocity does not change. Okay, for the Pelton wheel turbine, magnitude of relative velocity does not change. Mean that W1 equal to W2 for the Pelton wheel. But the direction of relative velocity uh, is different, okay, between inlet and outlet. Only the magnitude is similar. Okay, so only the magnitude, okay, but different different direction. So this different in direction of the velocity of the fluid jet causes a torque on the rotor, okay, resulting in a power output from the turbine. Okay, so as you can see here, Rm is mean radius. Okay, so Rm, as you can see here, Rm, which is Rm means that it is mean radius. Okay, which is Ri plus Ro divided by 2, which is defined as mean radius. So let's see the schematic diagram for the Pelton wheel. Okay, so this is the uh, schematic diagram. For this is the tangential, and then this is the radial. In this Pelton wheel turbine, no radial component velocity are involved. Okay, so no radial velocity component are involved. But if we recall the, for example, to find the torque produced from the shaft, we just need to obtain the tangential. Okay, so top shaft we need to obtain the tangential velocity v tangential 1 and then v tangential 2. Okay, so this is if we view flow as viewed by an observer riding on the Pelton wheel in terms of relative velocity. Okay, so this is inlet. Okay, velocity from the high velocity from the jet. Okay, coming from this direction, and then we have relative velocity w1 equal to absolute velocity minus with u, which is speed. Okay, u equal to omega r. Okay, and then this is the bucket. Okay, as you can see the bucket, and then we will have the deflection. Okay, deflection at this beta angle. Okay, so from this from this schematic diagram, we'll come out with omega 2 basically equal to omega 1. Okay, so uh, uh, same magnitude but in different direction. So mean that W2, which is relative velocity at 2, equal to V1 minus U. So the bucket will ideally turn the relative velocity, okay, W2 vector through a 180 degree beta, which is 180 degree turn, but physical constraint due to that beta, the angle of the exit edge of the blade is commonly less than 180 degree. Okay. Okay, so to calculate the torque and power, uh, we must know the tangential components of the absolute velocities at the inlet and exit. Okay, so recall your T shaft. Okay, torque produced from the shaft. We need the we need what we call the tangential velocity. Okay, so from this triangle A, which is at position 1 and position 2. 1 is refer to the inlet, 2 refer to the outlet. Okay, so since at inlet we are not concerned with any radial velocity, so that velocity, so this is tangential, and then this is radial. Okay, so at 1 no tangential, no radial velocity, so v tangential 1 equal to v1, okay, which is equal to w1 relative velocity at 1 plus with u. Okay, so there is the tangential velocity at 1. Okay, so at the outlet, so this is at the outlet bucket flow that deflected from the due to the bucket or due to the blade of turbine, V theta 2. So this is V theta 2. Okay, so see, this is V theta V theta 2. Okay, so V theta 2 equal to W cos W2, which is relative velocity at outlet, cos with beta angle, plus with the U speed, the blade speed. So with that assumption, W1 equal to W2, we can come out with V theta 1 minus V theta 2 equal to U minus V1 1 minus cos beta. Okay, so just W1 and W2. So W1 equal to W2. Okay, so we will come out with this equation. And then to obtain the power, or to obtain shaft torque from the shaft, which is m dot mass flow rate, or equal to rho q uh, rm theta 1 minus v theta 1 minus with v theta 2. So v theta 1 minus v theta 2. Okay, so v theta 1 minus v theta 2 from previous slide. V theta 1 minus v theta 2 equal to v theta 2 v theta 2 minus with v theta 1, which is equal to u minus v1. Okay, u minus v1 1 minus cos beta. Okay, so so this is v theta 2 minus v theta 1, outlet minus with inlet. Okay, so because mass flow rate at the inlet always negative, okay, mass flow rate at the outlet always positive. So we get T shaft for the turbine equal to m dot mean radius u minus v1 1 minus cos beta. Okay, or we can define omega power produced from the shaft, which is equal to torque shaft multiply with omega, which is relative the angular velocity for that particular shaft. Okay, so T shaft multiply with omega, we will get m, because omega the equal to u, sorry, uh, omega equal to 2 pi n, but u the blade speed or the bucket speed equal to omega rm. Okay, so we will come up with m dot u u minus v1 1 minus cos beta. Okay, so this is for impulse turbine, to find the power produced from the due to the flowing fluid. Okay, and then rotating the shaft. So this is what we obtain, w dot shaft, the shaft multiplied with the omega. So from this equation we can conclude that the power is a function of beta. Okay, so power is a function of beta. Typical value of beta for turbine commonly is less than 180 degree. So typical value of beta normally 165 degree. Okay, so this is how to obtain the work W dot power from power produced from the shaft to the shaft uh, for the turbine. So this is a typical theoretical and experimental power and torque for a Pelton wheel turbine as a function of bucket speed. Okay, so bucket speed. So this is bucket speed U equal to omega Rm, and then this is omega. This is a power produced uh, to the shaft, and then this is torque shaft the shaft. Okay, so we proceed to a second type of impulse turbine that commonly used in engineering application. Okay, so for the second type of impulse turbine, commonly the working fluid is gas. Working fluid is gas. So for this type of impulse turbine, as you can see, there are a lot of nozzle installed. Okay, and then very high speed velocity from nozzle. We rotate this bucket, okay, this bucket, and then produce the power to the shaft. Okay, and then for this kind of impulse turbine, it is commonly been used by dentists, uh, dentist drill turbine. Okay, so this is commonly being used by dentists. So for this kind of turbine, okay, for this kind of turbine, a series of fluid, okay, series of fluid jet strike the rotating blade, okay, so rotating blade, which as with the Pelton wheel, after alter both the direction and magnitude of the absolute velocity. Okay, as with the Pelton wheel, the inlet and exit pressure are equal. Okay, inlet and exit pressure are equal, and the magnitude of the relative velocity is unchanged as the fluid slide across the blade. Okay, so let's okay, so this is the velocity triangle for this kind of impulse turbine. Okay, so let's say we have a coming fluid from here. Okay, so you have nozzle. Okay, you have nozzle, lot of nozzle come. So let's say this is the absolute velocity from the nozzle. Okay, so as you can see, this is the bucket, and then this is the blade speed or the bucket speed. Okay, so this is section 1. Okay, for the inlet, this is absolute velocity, which is v1 coming from the nozzle, and then this is u, which is the bucket speed, and then this is relative velocity w1, and then at the exit. Okay, so because the at the exit we have v2, which is the absolute velocity for the exit, and then there are different direction of relative velocity w2, and then u2. Okay, so it's the same principle, relative velocity plus with the u, blade speed equal to absolute velocity. Okay, so this is the velocity triangle for this kind of impulse turbine. So in order to for the absolute velocity of the fluid to be changed, okay, absolute velocity of the fluid to be changed in this direction, uh, the blade must push on the fluid in the direction opposite of the blade motion. Okay, direction opposite to the blade motion. Hence, the fluid push on the blade in the direction of blade motion. So the fluid does work on the blade. So which is called as a turbine. Okay, so this is for the impulse turbine uh, that use nozzle that is use variation of nozzle. Okay, and then the last part for this chapter is reaction turbine. Okay, so reaction turbine are best suited for higher flow rate and lower head situation. Okay, so turbine can be categorized as follow, which is radial, mixed, and axial. So the same as pump. So typical radial flow, which is known as franchise turbine, and then typical axial flow, which is known as Kaplan turbine. Okay. Okay, so I think that's all for chapter 4. In the next video, I will show you some example for the turbine. Okay, so thank you very much.